Okay, welcome back, guys. Hope you had some success with last class's homework and with last class's video. Again, please let me know if you guys want to meet and talk about it. Happy to talk about anything. I know this stuff is definitely getting new and maybe difficult just in terms of the volume of new information that you've been getting recently. And so if you need to hit the pause button, please let me know. Happy to talk about it. Okay. We are going to push forward a little bit today and talk about polynomial approximations using Taylor-Maclaurin series. Good news is that we've already talked about this a little bit, and so this isn't going to be completely brand new, but I want to dive into this idea a little bit further, as it's probably one of the most important parts of this whole unit as to why series are important and how they can be useful. And so what do we talk about when we say polynomial approximations? Well, we've already talked about Taylor-Maclaurin series as a whole. We've actually already talked about Taylor-Maclaurin polynomials a little bit as well, which is basically cutting off an infinite series at a certain degree and saying, hey, that's the nth degree Taylor polynomial, or that's the nth degree Maclaurin polynomial. And so we want to be able to approximate some known function at a certain input value that is hopefully close to the center value in which that series is constructed around. Now, when going through these problems, the center value might already be picked for you, and the Taylor polynomial itself might not be constructed. And so there's two big parts to today's video. The first big part is actually creating and constructing a Taylor polynomial. You'll find that very similar to something we've already done. We're just going to do maybe slightly more difficult versions of it today. And then the second part is going to be finding the error associated with the approximations that we find using our Taylor polynomials. So a couple of things I want to point out before we move forward, and this is just some notation maybe. This notation right here, this piece of n of x, that stands for the nth degree Taylor polynomial. All right, so whenever we're doing a polynomial, instead of using the full series, you'll see this notation, meaning that we are cutting off the infinite series at some nth degree, and then we're going to actually plug an x value into that polynomial, get some output, and that output will be our approximation for the actual output of the function. All right, we're going to be working, and really we're just getting an idea of how all this works. Okay, so we are going to be working with functions that, yes, we can plug the actual inputs into the actual functions into our calculator. I'm just trying to answer the question of, well, why would we be using sine if I can just play? Again, we're just getting the idea down. All right, how can this stuff be used, or how might it be helpful in some way, shape, or form? So this notation P sub n is the nth degree Taylor polynomial. This n right here, this little guy right here, should match up with the derivative that you need to go out to, but more importantly, this degree that's next to the x minus c to the whatever power. So the x minus c to the nth. So that P sub n should match up with really your last term that you have. Okay. Those are just important parts. You'll see that a lot going through today, but I just wanted to spend a little bit of time on that. All right, let's kind of jump into this. I think doing this with an example, because we've actually already done this process before, is going to be a little bit more helpful than kind of going through more notation and jargon of that sort. And so here's what a problem might look like. We want to find the fourth degree Taylor polynomial of the natural log of x, that function, y equals natural log of x, centered at c equals 1. So we're actually not even doing an approximation just yet. We will eventually, but we just want to find the fourth degree Taylor polynomial. All right. Ln of x is not one of the four big functions that we've worked with. Getting to just ln of x is not easy using any of the four big Taylor series that we've worked with so far. And so we're actually going to have to construct this one. More so, it's not centered at 0, mainly because the natural log of 0 doesn't exist. So that doesn't make any sense anyway. But the Taylor series or the Taylor polynomial itself isn't going to be, it's not going to look as nice as, just some coefficient times x squared plus some coefficient times x cubed. That x minus c, or x minus 1 in this case, is going to stay throughout the entire polynomial. Okay. So let's start revealing things just a little bit. And I'm going to replace, this is the general form of any Taylor polynomial. If you remember when we did sine in the very first class, right, that we started talking about infinite series, we constructed a Taylor series for sine of x and actually a Taylor polynomial. This was the form we used, right? We proved that any Taylor polynomial can take this form. All right, so some key things to keep in mind. It always starts with just the regular function evaluated at the center value. All right, and then the first derivative, x minus c to the first. The second derivative at c divided by 2 factorial to the second. All right, and that pattern keeps rolling on. The biggest piece to remember is this, f to the n of c divided by n factorial. That is the coefficient to this term, x minus c to the nth. All right, that coefficient becomes very, very important. All right, so remember this coefficient, f to the n of c divided by n factorial. All right, let's replace that general form with our function that we're actually working with. Okay, so instead of p sub n, we want to find the fourth degree Taylor polynomial, right? So p sub 4 of x is equal to, we're using c equals 1, so I'm going to replace all of my c's with 1s. And so you just see that kind of carried through, right? All of the c's are turned into 1s. Everything else is exactly the same, all right? Except at the end, I'm not, I don't have this ... plus. I literally want to stop at the fourth degree, right? And the fourth degree is right here. See that exponent of 4? That means fourth degree. Okay. So now, what is everything that we're missing? Well, the 2 factorial, 3 factorial, 4, those are just numbers, so those are fine. X minus 1 squared cubed into the fourth. Those aren't going to change because I want to plug something in for x, so I'm not going to make x something and get an actual number there, so those are okay. The only piece that you really need to find here, which is why I said it's important to remember this coefficient because it's really the only thing you need to work with, are the derivatives of the function itself evaluated at the center value. And sorry, this should be a 1 right here, not a c. I'm just noticing that. Apologies there. So just change that to a 1 in your notes if you're copying that down. So you will literally have to actually construct all the derivatives and then evaluate them at your center value, okay? This is the natural log of x. Please go ahead and double check me here. If you want to take the fourth derivative, all the way up to the fourth derivative of ln of x and plug in 1 yourself, go for it. Pretty sure this is correct. Just remember that the derivative of ln of x is 1 over x, and then you have to continuously do sort of the chain rule going there, x to the negative first, and so on and so forth. All right. I'm sorry, the power rule, not chain rule, power rule. And then you actually have to evaluate all those derivatives at 1. If we do that, we get 0, 1, negative 1, 2, negative 6. Okay. Those values, 0, 1, negative 1, 2, negative 6, are going to replace these guys right here, f prime and 1, f double prime, f to the third, and f to the fourth. All right. And after I do that, I've actually already created my polynomial. All right. So it's really not that bad. All you're doing is taking derivatives and plugging values into that derivative and then replacing those values into your polynomial form. So here's what it would look like if you were to literally replace and just exchange, right, everything. Whoops, sorry, that was wrong. You can see where all the derivatives go. All right. And they literally just fall into place, which is nice. Okay, and so once you plug in your derivatives, now you've got all of your coefficients are actual coefficients, not notation. And you can simplify all of this down. 1 over 2 is 1/2, so that's just over 2. 2 over 3 factorial is 2 over 6, so that's 1 over 3. And then 6 over 4 factorial, 6 over 24, or just 1/4. All right, and so this is our actual fourth degree Taylor polynomial of the natural log of x, meaning that we can approximate any output of the natural log of x using this fourth degree Taylor polynomial. Obviously, if we would have went out further, approximations would have been better. Also, good to note, we centered this at 1. So if we start plugging x values into this approximation that get further and further away from 1, especially with small values of the nth degree, then the approximation is going to be much, much worse. Okay. So the reason for centering or picking a center and constructing a new Taylor polynomial from a particular center is because you probably want to approximate the function around that center value. All right. But here is our actual Taylor polynomial, fourth degree Taylor polynomial for the natural log of x. Okay, I have one for you to try on your own. I want you to find the third degree Taylor polynomial for y equals cosine of x, centered at c equals pi over 3. So yes, you will have to find 3 derivatives of cosine, plug in pi over 3. It's only nice because obviously cosine's derivative of sine, and then that just alternates. Just watch your negatives, all right? You have to have some negative signs put in there. And then plug everything into this general form down here and simplify. Pause video, come back for the answer. All right, hope you had some success there. I'll reveal the answer and the solution, and we'll just walk through it kind of quickly. So here are my derivatives. Again, double check me here, but pretty sure I'm good. And then I'm just plugging pi over 3 every single time into the successive derivatives, right? And then the actual function itself. I'll take those values, those derivative values, and actually attach them to the coefficient for the Taylor polynomial. So here's your first degree. That's really technically over 1 factorial, but we don't need to write that. Then you've got your negative 1/2 over 2 factorial, and your square root of 3 over 2 over 3 factorial. And then you can simplify all of that down to here. Okay. So this polynomial would represent or approximate cosine for values that are close to pi over 3. Right? And so that's the next slide I want to show you, because I know we've had some questions about the center value, and it does get a little bit confusing as to why we're calling it that or why we're even using center. It's because you can do this, right? So typically we're using 0 or 1 or something really easy just to have something to work with, but that center value is important, and how you choose your center value should make sense. Again, why are Taylor polynomials used? To approximate functions at certain x values. Well, if I'm using a polynomial for a certain x value, I want to construct that polynomial close to that input value. So here's what I mean. If you take cosine, which is this red curve, all right, so this is the actual cosine curve. This is cosine of x. And then you start building successive orders of Taylor polynomials. This purple line is the first degree Taylor polynomial, all right, of cosine. And then the second degree and the third degree, so on and so forth. I actually centered all of these around pi over 3. So this line over here is x minus pi over 3. The black one is the second degree. All right, so x minus pi over 3 plus x minus 3 to the second divided by 2, so on and so forth. This down here, right? It was this guy. Sorry, 1/2 minus square root of 3 over 2 times x minus pi over 3 minus 1/2 divided by 2 factorial x minus pi over 3 squared, and then the last one I did was to the third, right? So the blue curve is the third degree Taylor polynomial of cosine. So that's the one you actually just did. And so if you look at it, though, as you get further away from pi over 3, which is really close to 1, right? So pi 3.14 divided by 3 is really close to 1. As you get further away from x equals pi over 3, the approximations, meaning that the curves that aren't the red curve, get further and further away from the red curve. The blue one is the third degree Taylor polynomial. So that one should be as close to cosine as we have on this screen. And if you can follow it, right, so just kind of blur out the black and the purple lines and just look at the blue and the red, the blue line stays closest to the red line as you go left or right of pi over 3. And so that approximation is going to be better. But you can see that the blue line does start to peel away from the red as you get further away from pi over 3 on both the left and the right. Okay, so using a third degree Taylor polynomial centered at pi over 3 to approximate, I don't know, like cosine of 5 probably isn't a good idea, because cosine of 5 is like somewhere right around here. And look how far away that output would be from the actual output. As opposed to at pi over 3, the blue line is pretty darn close, if not, it's almost exactly the red line. So that's why you want to do that. Just a little bit further explanation of why you want to create a Taylor polynomial around a certain center value. Okay, so next thing I want to talk about is error. I want to just make a quick note. There are two types of error that we're going to use. The first one has to deal with alternating series, which I'll talk about in just a second. The second one does not. We are only going to very quickly touch on the second error bound tonight. Or today, sorry. I'm recording this tonight. And then we're going to get further into it on the next video. Okay. So let's jump into an example of using error, and we'll be able to get a good idea of how we can do this and how both of these are going to be used. Okay. So I want to go back to the Taylor polynomial that we first created using the natural log. And really what I want to do is actually start getting approximations. Okay. So I want to be able to approximate the natural log of 1.1. Again, can you put that in your calculator and get the actual value? Yes. We're just showing how this works and how it can be used. All right. So my first task, use a third degree Taylor polynomial to approximate natural log of 1.1. The second thing I want to do, because it's an approximation, is I want to be able to bound the error. I want to know, how far off I am from the actual output. And so these questions are asked in interesting ways, I suppose. And so I just wanted to show you again, maybe this is kind of some more notation showing more than anything else, and as to how you'll be asked about the error. And so the first way it might look is this, right? We want R sub 4, which stands for the remainder when using the fourth degree Taylor polynomial. And excuse me, I'm actually going to change this because I do want to do a fourth instead of a third. So using a fourth degree Taylor polynomial, the remainder of an input 1.1, I want to know that that is less than 0.000003. Okay, so is the remainder when using a fourth degree Taylor polynomial with an input value of 1.1 less than this value? We'll be able to figure that out. Another way of saying the exact same thing, just different notation, is the fourth degree Taylor polynomial a value at 1.1 minus the actual function. So if you could evaluate the actual function, which is the natural log, at the same input value 1.1 less than 0.00003. Right. Again, notice the absolute value because we're talking about a max error on either the plus or minus side. Okay. So saying the same thing, we're just trying to figure out what the maximum error is if we use a fourth degree Taylor polynomial. More specifically, for this problem, we want to prove that it is definitely less than this value. Okay, so first thing we'd have to do, if we were starting completely from scratch, which we won't just for time's sake, is we would have to construct the fourth degree Taylor polynomial. We already did that in the first example, so we're ahead of the game here, but you might have to do all this in one. So fourth degree Taylor polynomial for a natural log, here we go. We already found that. What would I want to do now? Well, I want to approximate 1.1. So I'll replace x with 1.1, and as you see here, and I'll actually find the value. Right. So P sub 4 1.1 is this number right here. So that's my approximation. How close is this number to the actual output of natural log of 1.1? Well, we might not be able to find the exact error, right? Because if we knew the exact error, then there would be no reason to even do this approximation. But what we can do is find the maximum error, right? And so at this point, when you're doing any of these problems, so this is what I was saying we were going to get into. The first thing you need to ask yourself is, what type of series is it? Is it alternating or is it not alternating? If it is alternating, you're in really good shape because you've already done this before, right? We've already, we just took our last quiz on this. You're still going to use the next term in the series and input the same value into it, right? So we talked about alternating series already. We stopped at a certain degree, and then we just use that next term, whatever it might be. We are going to do the exact same thing. So for alternating series, it's sort of status quo with what you've already done. All right, and I'll show you that in just a second. If it's not alternating, we're going to use a Lagrange error bound, which again, that's what we're just going to touch on tonight, or today. Sorry, again, doing that. And we'll get into that a little bit more later. Okay, so let's continue the example. So since it is alternating, all right, we can clearly see the series is alternating. You could go out further if you'd like, but it definitely alternates. All right, once we know that, the only thing we need to do is figure out, well, what would have been the next term, right? If we were to take a fifth derivative and plug in our center value and find the coefficient and simplify so on and so forth, what would it have been? You can see here we got lucky that there's a pattern, okay? And so the Taylor series for the natural log does have a nice pattern. And so you can kind of see that we're just going to have the third divided by the same value. So to the nth divided by n, x minus c to the nth divided by n. So since the series is alternating, the next term would be what? A sub 5. So this means just the next term. Okay, not the whole thing all the way up to 5, but just this term itself. 1.1 minus 1 to the fifth divided by 5. This number, which I have right here, is your maximum error. Okay. So if you were to calculate 1.1 minus 1 to the fifth divided by 5, we get this decimal. And so what that tells me is the remainder for the fourth degree Taylor polynomial at 1.1 is definitely less than or equal to, because this was the maximum error, 0.000002, which is definitely less than the number we started with. So we're good. Okay. So again, alternating series, pick the next term in the series. If you see a pattern, you can use the pattern. If you don't see the pattern, you'll have to actually find and construct this next term and plug in your input value. But hopefully there's a pattern and it's a little bit easier. Okay. All right. So want to try on your own. So we're going to use a cosine approximation here, and I made it a little bit easier on you because I want you to find fourth degree Taylor polynomial centered at c equals 0, which is really just the Maclaurin polynomial in the Maclaurin series for cosine, which we've already worked with a ton, and you can go back in your notes and get that. And I want you to approximate cosine at 0.1. All right, so let me just put a 0 in here just so you see that. It's 0.1. And then furthermore, I want you to show that approximation using the fourth degree Taylor polynomial minus the actual function evaluated at 0.1 is less than this decimal. Okay. Pause the video, give it a shot. All right, let's take a look at the answer. So here is my fourth degree Taylor polynomial for cosine. Hopefully that's familiar to you. What I want to do is take that polynomial and plug in my input, so 0.1. If you use a calculator, you would get this nice long decimal. And so this is my actual approximation. So I just checked off sort of the first part of the problem. Now I want to find the error associated with this approximation. Cosine, I know alternates. It's in the actual series itself, -1 to the nth. And so I can use the alternating series error. And so the maximum error or remainder for a fourth degree Taylor polynomial is going to be less than or equal to the next term in cosine's Taylor series. In this case, it's x to the 6 over 6 factorial. And so I want to take this term, plug in my input value that I use for the approximation, and find the actual decimal. If you did that, you get this nice long decimal, which is definitely less than the value that you were asked to find. So we're good. Okay. All right. Hopefully you had some success with that. Let me know if you did not. Okay. So this is the Lagrange error bound. What I'm going to say is I need you to definitely trust me for part of this, because this is maybe one of the more confusing pieces that we'll talk about through the year. But what, again, I'm going to walk you through it and try and make it as easy as I can. There is a part to this that I'm just going to sort of give to you. I'm happy to talk to anybody about a further proof or a further explanation if you want to get into some sort of more advanced math. But I'm going to try and, like I said, just give you a baseline today, and we'll work a little bit more with it a little bit later. Okay. So this is for the error associated with non-alternating series. And so when I have a non-alternating series that I'm actually approximating, I want to use something called Taylor's theorem. And it's the same Taylor as Taylor polynomial. He worked with series a lot. And basically what it says is this. And so this makes sense, right? If I have some function and I can use approximation, so up to some nth degree Taylor polynomial, the actual function is equal to that approximation plus some remainder, right? Some number. Right, and this is what we're trying to find a maximum of. But if I knew the exact remainder, then I would get the actual function itself. Now, Taylor proved, and so this is where I want you to at least trust me, or trust Taylor if you want, and you can look this up online. Taylor actually proved that the remainder is equal to this strange term right here. And so, yes, it looks familiar based off of everything that you see up top here. What are the big differences? Well, I'm not going to the nth. I'm going to the n plus first derivative and the n plus first factorial, and then the n plus first degree. Okay, so very much so like alternating series, I'm just going to sort of that next term. But the biggest difference is that I'm evaluating the n plus first derivative of f at z. So hopefully your question is, well, what is z? Z is some number in between x and c. All right, it can actually include x and c as well. All right, so there's some number in between x and c such that if I took the n plus first derivative of f at that value and filled out the rest of this term, I would find the actual remainder. Again, if you want to look at the proof, go for it. It's a little bit involved. Happy to talk about it further if you'd like. So what does that mean for us? Because, again, we can't use this because we can't actually find z. If we knew z, then we knew the error. If we know the error, then there's no point in doing the approximation. This is where Lagrange's error bound comes into play. So a result of Taylor's theorem says this. Well, if that's true, then the maximum error for the nth degree Taylor polynomial has to be equal to x minus c to the n plus 1, so that doesn't change, divided by n plus 1 factorial, so that doesn't change, multiplied by the maximum of the n plus first derivative evaluated at z. All right, so that's where it starts to get a little bit weird. All right, so let's jump to the next slide, and I'm going to try and explain it just a little bit better. So the first bullet I already talked about a little bit. Similar to alternating series, we're just using the next unused term, hence the n plus 1 you see all around Taylor's theorem. The biggest thing that we want to get our head around is this z value that I actually have to evaluate the n plus first derivative at. Typically, we do that at the center. It may or may not be the center. So z may or may not equal c. That's something we might have to determine along the way. All right. Since the remainder is actually equal to that term that you have there from Taylor's theorem, right? The only value that we want to choose is the value that maximizes this part right here, this derivative. So if I have a center value, let's say 0, and I'm actually and I want to approximate a function at, let's say, x equals 2, I've got an entire range from 0 to 2, including 0 or 2, that I can plug in to the n plus first derivative of f. Whatever value in between 0 and 2, including 0 and 2, maximizes that derivative. So whatever the highest value I can get out of this piece right here, that's the input value that I'm going to make z equal to in our case for the Lagrange error bound. All right. It's not necessarily the exact same z that gives you the exact error, but I want to pick a value such that I maximize this term. All right. Because if I maximize this term, then I maximize the entire error itself, right, which is what I'm going for. Hopefully that made sense a little bit. Happy to talk about that more with you, certainly. Here's a quick example. Again, we're not going to get into this a whole lot more. All right. And it's actually, as you'll see, kind of a silly example, but I just want to wrap your heads around this a little bit. What I want to do is approximate e, right? So e to the first, the actual number e, using a second degree Taylor polynomial centered at c equals 0. So in this case, I'm using e to the first. So the input value that I want to use for approximation is 1. I'm centering my Taylor polynomial at 0. And so it makes sense to use the e to the x Taylor polynomial or Taylor series. And so I put that right up here. And so the first steps are exactly the same for the approximation. I actually want to find the fourth degree Taylor polynomial for e to the x, which is right here. Hopefully that looks familiar to you at this point. Second step, I want to approximate the Taylor polynomial at 1. So if I plug in 1 into this polynomial, I get this number, 2.708333, which is really close to e itself. Okay, so that's actually pretty cool in itself. Next step, I want to find the maximum error associated with that approximation. Notice that the polynomial is not alternating, so I can't use the alternating series, right? I can't just plug in 1 to x to the 5th over 120 or x to the 5th over 5 factorial, all right, because it's not alternating. That is not valid for this polynomial. So I have to use the Lagrange error bound. So here it is right here. This is what you want to remember, all right? This is what you want to know, this piece right here. This is the big part, all right? Notice that I can pretty much plug in everything except for this last piece, right? The z value. I don't know what z is just yet. But everything else you know, right? X minus c. Well, you know c is equal to 0. X is equal to 1. N is equal to 4, right? Because I went to the fourth degree Taylor polynomial. So everything else you can plug in, and we'll simplify as much as we can until we get to this part that we can't do anymore. All right, so here's that simplified version right down here. You can follow that. And so now let's really just concentrate on this max x to the 5th of z. So typically, like I said, you can't actually find the z, but we can find the maximum, all right? And so the places that you most want to look on that interval are the endpoints, right? Or your x value and your c value. So, because typically that's where that maximum value occurs. It's not all the time, so we'll talk about a few special cases, but a lot of the times, because we're talking about continuous functions that either increase or decrease, especially on a small interval, the endpoints are the places that you want to look the most. So the first thing you need to do is find the actual fifth derivative of the function. Ours is easy, nicely enough. So the fifth derivative of e to the x is e to the x itself. Then I want to start to just kind of analyze the derivative. I know e to the x increases on its entire domain. So this one's going to be kind of nice and easy in terms of finding the maximum value. But just to show you what I would probably do for most cases is evaluate the derivative, the n plus first derivative at c, so at 0 in this case, and then also at x, or 1 for us. Figure out which one of those two is bigger, and then most of the times you're going to use the larger one. Okay, so for us, again, this is why the example is a little bit silly, but so the fifth derivative of e evaluated at 1 is e itself. So here is that maximum derivative value that we want to use. I'm saying it's silly because, yes, I'm using e as a maximum error associated with an approximation for e. Again, just trying to wrap your head around it, all right? And so now I'm going to use that value, whatever that maximum derivative value was on that interval, inside of the remainder theorem or the remainder formula. Okay, so here's that 1/5 over 120. That's what we found before we talked about the max derivative. My max derivative is e itself. So if I multiply e by 1 over 120, I get this value right here. Okay, and so that is my maximum error that's associated with my approximation that I found for p sub 2. That should say, I'm sorry, this should say p sub 4 right here. All right, that should say p sub 4. Apologies. All right, hopefully that wasn't too bad. Again, happy to talk about that. Happy to get questions about that. All right. So here's what's to come. We still have more in Lagrange error bound. I want to talk about that a little bit more, especially some special cases. We'll talk about it. And then finally, the last thing that we'll talk about is combining it all. Right. So we're going to basically use or construct a Taylor series to create another Taylor series by operating on it using addition, subtraction, composition, differentiation, integration, so on and so forth. We're going to take those new series. We're going to find approximations for certain input values. And then finally, we'll use either error, whether it's alternating series or Lagrange, to talk about the maximum error associated with that approximation. And that pretty much wraps everything up for us, which is exciting. We're almost there, okay? Homework will be on by Malvern. Have a great day, guys. I'll talk to you soon.